Hey kids, so here's what I was talking about last week. We started with the phase diagram, and we talked about how if you look on the x-axis, you have temperature, and on the y-axis, you have pressure. So it made sense to you that if this is phases, shows states of matter, that which of the three states of matter, solid, liquid, or gas, would you find at something where there's temperatures are low, right? Low temperatures here, and then very high pressure. So they're pushing all the particles close together. And many of you realize that that's the solid, which is great because then you don't have to memorize anything. You already know it. And then alternatively, if you had very high temperatures and pressures that were comparatively lower so that the particles were more spread out, you realized that that was going to be a gas. So this area is the gas, and that represents where the gas is. And then in between, it's no surprise that that would be liquid. So we did all this to explain how this therefore shows that at certain pressure and temperature, you'll be able to figure out whether it's a solid, liquid, or gas. And then this line here that goes between liquid and gas, this would be representative of sort of boiling. And this line here that goes between solid and liquid would represent melting or freezing. So, and then we took that a step further. I think I started showing you water. And we talked about how, according to this then, so if this is the normal boiling point at 1 atmosphere pressure, then if we could reduce the pressure to say here, then theoretically water would boil at a lower temperature, right? Lower than 100 would be somewhere here. So I don't know what that is, but so we made the observation then that in theory you could boil water at room temperature if you could get the pressure down low enough, and that's what I did in the vacuum. I was able to boil water in the class at room temperature by decreasing the pressure. So and that's true with freezing point, right? In this case, since this is water, you would decrease the pressure and you would be able to freeze actually at a higher point here. It would take a higher energy level to freeze the water, or a higher temperature. Not much though, since that's 0.00 and that's 0.01. So anyway, we didn't really get into that, and we shouldn't. So the normal freezing point and the normal melting point are found here at point B, and the normal boiling point is found here at point C. And normal just means it's at 1 atmosphere pressure. The triple point is where all three things exist together. And so that's A, where solid, liquid, and gas. Remember, this side is solid, this side is gas, and then in between is the liquid. So solid, liquid, and gas all exist at the triple point. The critical point is up here, and that's the point where only a gas can exist. I'm not a fan of that myself. So, and then so this is a helpful graph for that reason. It can kind of tell you how you can manipulate pressure to get different phases. So let's discard that for now. We'll discard that. And then if we look back here, so then I should have shown you this, and I showed some of you this, but this is the triple point of hexane. Or not. Oh. That's weird. All right, so what this will show you is this is a liquid right now, and then they're pumping on it, and then you'll start seeing all three phases exist: the gas, liquid, and solid. So there's the solid of cyclohexane, and then it'll start boiling, which will be a liquid and gas phase here in a second. Here in a second. There it goes a little bit. I really should watch these before I share them with you. There it is. So, yeah, and then it freezes and it boils. And it's what we call is the triple point. So all three things start existing all at once. So it gets to be a solid, and then it bursts into liquid and gas. And then it goes back to solid. And Isn't that amazing? Science. All right, so I actually, old whatever, added another thing here. So hopefully I'm still recording. Seems like I am. All right, so moving on. Let's move on. So we talked about then the reason I could boil water at room temperature by lowering the pressure is because boiling is actually defined as the temperature at which the vapor pressure or the pressure of the particles that make up the liquid that are coming into the gas phase are equal to the atmospheric pressure, the pressure that's pushing down on them. And if you think about this, a molecule or or a particle in the liquid has to be moving in the right direction and with enough speed to actually break away from the liquid. And that's great. And this is like, I'm free. But then there could be a atmospheric gas molecule that knocks it back in. And so if we take away some of these atmospheric molecules, it's easier for things to boil because there's nothing knocking them back into the liquid. So now all they need is the right direction and energy to leave the liquid, and then there's nothing to knock them back in. So that's why that the guy very high up on this column of air that exists on Earth would have very few air molecules knocking things back into the water. And then if he were trying to boil something lower, now you can see there's much more molecules of atmosphere knocking things down. And if he's doing it on sea level, now there's a lot more molecules of air from the atmosphere pushing down on him as well as the water. So because of that, water at sea level will boil at 100, and as you go up the mountain, the boiling point will be less and less. And in an airplane, it's even less than that because it's not got as much of an atmosphere to fight the higher up it goes. So this is why if you've read on your pasta or your mac and cheese, it says if you live in high altitudes, you might have to boil something longer because it can't give you all the heat that you need to boil something in the time specified at sea level. All right, so that's done. And then the last thing we were talking about was how turning a solid to a liquid. So if you have close packed particles in a solid, and then you give them a little more energy as a liquid, a little more flowiness, that means you have to put energy in it. That's endothermic. And then to be a gas where they're really separated, that's even more endothermic. To become a liquid, from a liquid to a gas, you got to spread those things around more. So that takes energy, and going backwards releases energy. So that's exothermic. And then, to nobody's interest, but I'm still going to push it down your throat, we talked about how air conditioning works. And air conditioning works using that. So when I boiled water at room temperature, you felt the bottle, the flask, and the flask was cold. And it was cold because it is an endothermic process to go from liquid to gas. And because of that, it'll take heat from wherever it can take it. We're not heating it on a stove. We're just in a room temperature room. So it just took the heat out of the room. And because it took the heat out of the room, the flask became cold. And that energy from the room was making the liquid turn to a gas. So air conditioner works on that very concept. It has a refrigerant running through a pipe, and in that pipe in the house, it's a liquid and it turns to a gas. And as it turns to a gas, it needs to pull heat in because turning from a liquid to a gas requires heat. That's an endothermic process, and it pulls heat from the room. And as a result of pulling heat from the room, the result is that the coils become very cold. And since they become very cold, you blow a fan over them, and it blows cold air out. So that's how air conditioner cools your house. It's pulling the heat out of the house by turning from a liquid to a gas. And in doing that, it gets very cold on the coils, and then you blow a fan over the coils and cold air comes out. Now what happens? So now we have this gas in the coil, and the gas goes into a compressor. And as I did in your class with the carbon dioxide, where I pushed real hard and I was able to turn gaseous carbon dioxide into a liquid, that's what this compressor is doing. It's pushing those gas particles, right? Those gas from far apart to really close together so they can be a liquid. And in doing that, it has to take energy out, right? For gas to become liquid, gas has a lot more energy. They're flying around, they're free, they're happy, they're like, wee. And to get them all kind of bound up as a liquid, energy had to come out of them. And the energy comes out as heat. And because of that, the coils now are hot because you turned a liquid to a gas to a liquid. And in turning gas to a liquid, you had to take heat out. And so these coils get very hot. And those are the ones outside the house. And that's where you see that big fan thing outside your house. And it blows a fan over that. And you have hot air coming outside the house. Now that liquid goes back in the house and becomes gas. So it gets cold. And then it gets compressed back to a liquid. It gets very hot. So the hot keeps going out of the house and the cold keeps going in the house. And the same thing with a refrigerator. You would have in the refrigerator the cold part, and in the outside of the refrigerator the hot part. And you would just keep the cold staying in the refrigerator and the hot coming outside the refrigerator. I think that's all fascinating. And just as more trivia, what they use in air conditioners right now is called R401A, which is difluoromethane, meth meaning one carbon, and difluoro, so there's two fluorines and one carbon. And they also have pentafluoroethane, pentafluoro meaning 5 fluorines, and ethane means 2 carbons. So that is what they've determined will not hurt the ozone layer right now. So then the other thing we talked about was colligative properties, which is the same situation. Take that back. It's a similar situation. God, this is much too long a talk. But I don't care, because what else are you doing? You're listening to me. All right. I should have had this. States of matter, fat. Should have had this loaded up, but I didn't. But it's too late now to get your money back. Semester's paid for. All right. So going from a liquid to a solid needs to sort of make that liquid fall into a very nice, what we call lattice, right? And with water, it's even more so. For liquid water, as you can see here, to turn into a solid, you need to start having the hydrogens, which are positive, attracted to the oxygens, which are negative, and lined up and such, as you can see. So there's a very specific order to the solid, and it needs to be very distinct, the sort of position everything takes. And because of that, if you dissolve a salt into water, as we do on snowy days, that salt is going to get in the way of those things falling into their perfect places like they want. And because of that, more energy needs to come out for them to become a solid. So this is a nice solid here, and this is sort of not yet there. Not yet a solid. So it needs more energy removed, more things to slow down so that they can become a solid. And that's why we salt the roads in the winter. By putting these salt things in the road, they dissolve in the water, and now it's harder for the water to form its perfect little solid lattice. And because of that, it takes more energy to pull out of that water to make it a solid. And so the ice melts and won't refreeze until like minus 15 Celsius, maybe higher than that. But basically, it buys us some time so that we don't have to get that cold. We usually don't get that cold, so our roads stay as watery, which is good for us. So, and then the analogy I told you is if I give you a bunch of Legos, right? Legos fit in a perfect way where there's, I didn't do a good job. Oh, wait, maybe I did. Nope, I didn't. All right, so there's a Lego, and then maybe this time. Nope, did a wrong thing again. Right, so Legos fit in perfectly where the part with all the dots goes into the flat part of the one above it. Kind of like water, where water needs an oxygen, and here are the hydrogens. So it needs a hydrogen bonded to the oxygen, right? That's how they line up in the solid phase. So if I gave you a bunch of Legos and told you to put them together on your desk, that's easy. But if I gave you a bunch of Legos and told you to put them together like in a sandbox or in a ball pit, it's going to be harder to put them together because now you have these particles that are getting in the way. So dissolving salt into water, any salt, doesn't have to be NaCl, anything that'll break up into pieces like this. So what they actually use, I think, is calcium chloride, because that'll break up into calcium and 2 chloride minuses, which is now 3 particles. Anyway, all right. So the same thing happens with boiling. Similar thing. So if you throw salt into boiling water and that salt isn't going anywhere, right? It's not volatile. It doesn't want to boil. So if you're looking at this molecule to get out of here and then fight the atmospheric pressure Now, instead of just being able to fly out around another water molecule, it's got this thing that's not going anywhere, this salt molecule that's just stuck. And because of that, now it can't go that way. It's got to have a special thing. So these salt atoms are making it harder for the water molecules to escape and boil. So because of that, adding salt increases the boiling point and it decreases the freezing point. So if we go back to this thing, what it's going to do then, since it increases the boiling point, the liquid is less likely to become a gas. And since it decreases the freezing point, the liquid is less likely to become a solid. So what you've done is sort of increased the area of liquid that's available by adding salt to that liquid. Now, again, remember, it has to be non-volatile for this to work, because if these are like an alcohol that want to leave, that have a lower boiling point than water, then they're actually getting less in the way of these water molecules than if there's something that doesn't want to leave, like a salt, like a solid. All right, and that's all I decided to do with that. And then I guess that was all I talked about. So that was the first talk on Friday. I hope that made some sense to you.